Okay, let's solve the question. High-speed electrons are directed at nuclei X. A graph of variations of electron intensity with diffraction angle theta is shown for nuclei X. The minimum intensity occurs at when theta equals to a theta mean. So we can see that the vertical axis here represents for the electron intensity. If we have it high, it means that there's a lot of electron shooting arrive at the string at that spot. But if it's low, it means that there's not much electron under that angle. Okay? Let's say electrons of the same speed are directed at nuclei Y. Okay, so we have another nuclei which have double the diameter of nuclei X. So seems like Y is larger than X. And they ask us for the nuclear density of Y and the angle as well. So first for the nuclear density, if you recall this equation, R equals to R naught, A to the 1 of over third. This is the equation to determine the radius of a nucleus based on the Fermi radius. Okay, so basically here there's an assumption that the nuclear density is always the same, okay, always constant for all elements nucleus, okay, because we have it equals to mass of the nucleus divided by the volume of the nucleus, and then we assume that if we have more mass, then that would be like more nucleon. A is the number of nucleons in the nucleus, and then this one also proportional to the volume. So that's why if you check this equation, when you see this equation in the data booklet, remember that it implies that you have the nuclear density as a constant. Okay? So basically now we can see that there's no way to go with option C or D, okay? Just A or B, because we have the nuclear density always the same. So that would be equals between X and Y. Now, for electron diffraction, if you remember, you can actually this question requires to have a look back at the equations here, diffraction for wave at C3, okay? And in under the topic E2, this is E2 topic, we consider that electron can be modeled as wave, okay? That's why it also have a electron diffraction. And that would be the same equation as well. It's just that for now, the lambda, the wavelength for electrons should follow the Broglie lambda, which is defined by the Planck constant divided by the momentum. Momentum equals to mass of the electrons times with the speed. And in this case, they say that the speed that directed at nuclei X and Y are the same, okay? Same speed, so it means the same lambda. And if it's the same lambda, so then it means that we have the left side to be equals, right? So let's just write it down here that n lambda x, okay, equals to n lambda y. Sounds good? And also then we have like this one also equals to dx times psi theta x equals to dy times psi theta. Oh, my bad. Psi theta y. So now see, easy now, right? So if we got the dy is double as dx, we can just have the ratio right now. Whenever you see something like double or like comparing, ratio is the best way to solve these kind of problems. And then you can have this one that should be theta psi x, right? And theta y here. Okay, so here it shows very clearly that x is greater than y. So it means that the theta should be decreased, and then the option that we should choose is option A. And now I just want to review a little bit about the electron diffractions. It means that if you got a cathode and cathode will when it got heated, then it can produce an electron beam, and then the electron beam pass through the crystal here. The crystal is basically the X or the Y element, and then we can see that just like diffraction, you got two nucleus like S1, S2. They are separated by a d distance. Then the wave, the lambda, okay, the broad wave travel to P here, and another lambda travel from nucleus S2 to the P here. So that at P there will be a resultant wave. That's just like the sum from these two waves. And then there will be a path difference. So if you want to check why the path difference, how can we derive this equation? Just check out the previous videos that I made before to explain about why we got this equation for diffraction for wave phenomenon in general, okay? And then here there's also an example. You can see that the electrons are emitted from a heated cathode and are incident on the crystallized sample of graphite. Then you can see the pattern here, okay? You see there's a really bright spot here, see? And there's some dark fringe around here, okay? So that's the P points that we want to show here. Usually it will be the dark fringe of interest, okay? And another point I want to emphasize here is that if we increase the voltage, okay, then we can have a faster electron, a higher speed, okay? So by controlling the voltage, then you can control the speed of the electron, and it means that you can change the lambda here, the broad wavelength of the electron. Okay, let me know if you have any question. Thank you.